Grazie Fabio, buonasera a tutti. My name is BOZZINI. I am here for the Swiss Federal Institute for Forest now and Landscape Research, WSL. And this is the agenda. I will speak about the monoplotting project and the monoplotting principle. Then some field of application and a couple of examples. And at least two advanced features that I have developed last year. So to the monoplotting project, the WSL monoplotting project began in 2010 with the goal of finding a way to use oblique photographs, particularly historical photographs, for quantitative landscape study. In other words, we wanted to make cartography with point landscape photography. This would have made it possible to do landscape research with the millions of photographs available starting as early as the second half of the 19th century in many archives. The project led to the development of a software that allows oblique photographs to be used to do 3D GIS. A start point of the monoplotting principle are the collinearity equations. Solving these two equations allows the usage of terrestrial oblique photographs to do cartography. The theory is nothing new. We just tried to make it useful, implementing it in the WSL monoplotting tool. I will not go more into details. This is just to show that behind all what we will see in the next slides, there is a mathematical approach. Actually, the concept is quite simple. We have three main components. We have the camera. In fact, this is a mathematical model that represents the original camera. We have the picture and the digital elevation model. The setup of the system consists in placing the camera and the picture in the real space so that choosing a point on the picture and tracing a ray from the camera through the point, the ray will intersect the DEM at the corresponding real point. This procedure, so-called camera calibration, ensures the correspondence between each pixel of the picture and the related point in the real world. In order to calibrate the camera, we need at least 5 control points that are points for which the correspondence on the photograph and in the real world is well known. The real point can then be represented on a geographical map. When the camera is calibrated, the image is georeferenced and becomes a 3D map. Now to the field of application with a couple of examples. The main fields of application include landscape evolution, for the reconstruction of the landscape dynamic of forests, glaciers, urbanization, and so on, for archaeology and history, to regain disappeared or no longer recognizable elements of the landscape, such as roads, trails, or buildings. Then we can use the program for the reconstruction of natural events, such as floods, landslides, or avalanches, and finally for the monitoring of natural events. The first example concerns avalanches. The month of April 1986 broke all records in Canton Ticino. We had 25 days of uninterrupted rain with extraordinary amounts of precipitation for the season. In the alpine valleys of Upper Ticino, 3 to 5 meters of fresh snow was measured, resulting in countless avalanches. Due to the huge number of events and the short duration of the traces of these events, the Forestry Service of Canton Ticino decided to systematically record the avalanches from helicopter flights. On the left, we have one photo with the digitization of the avalanches, and on the right, the cartography of these avalanches on a Swiss national map. The next example shows the evolution of the Botafogo area in Rio de Janeiro. This is the situation at present. Botafogo is this region. These instead are the current boundaries represented on a photograph of 1910. In Rio, in the past many hills have been destroyed, and the material has been deposited in the sea to gain space for the city. This photograph is no longer possible today because the hill from which it was taken is no longer there. This is the comparison between the two photographs. I would like to remind that everything shown is accurate GIS quantitative data, and it's not just a qualitative representation. Now to a couple of advanced features. The first is auto-rectification. Auto-rectification is a functionality that can be useful in at least two cases. The first case concerns single aerial photos that are nearly orthogonal, and historical photos are an example. Another case concerns, for example, photos from drones. If you want to get information quickly at low cost without requiring 3D reconstruction. This is a 1934 aerial photograph of a village in southern Switzerland, with on the right the corresponding auto-rectified and georeferenced image. The deformation is due to the irregular terrain of this mountain village. The auto-rectified image can be used immediately in any GIS system, like ArcGIS or QGIS. I will try to show you an online example. You can find this example at the website i2w.ch. And here you can play with the image. You can swipe between the two images and show. And you can get, depending on the photograph and on the orthophoto and the digitalization model, a quite good accuracy. And go back to the presentation. The next feature is rephotography. Rephotography has been a common theme in recent decades. Comparing past and present is the subject of several scientific research in different fields. In this example, we see the comparison of the Zurich spatial area between 1910 and today. The photo on the left was taken by Edward Specterini, one of the first aerial photographers of the history. He was shooting the photos from a hot air balloon. The comparison with today could be made by taking a photo from the same point, for example, from a drone. But monoplotting allows you to calculate the position and orientation of the camera. So the simplest, the most important for me, the cheapest solution was to simulate a today photograph with a Google Earth image. And the reprojection feature of monoplotting allows two images to be superimposed pixel by pixel, obtaining two images with the same dimension and almost perfectly coincident. I have also for photography an online demo, always on the same website. You can click this tower, just tower, to see the precision of these two, of this reprojection. Is the Google images was reprojected on the old picture of spectator. So if you can find more information on wsa.ch/monoplotting or on the website i2w.ch. This is the name of a startup I will find in the next days to promote the last and the next development of this software. So the WSL monoplotting tool became the image to word software. Thank you.
Yeah, my name is Mauro. I'm also working at the remote sensing group at WSL in Bermensdorf. And we are, in the context of this workshop, quite end users of the products you have done, and we can strongly profit from your work. So I want to tell you something about the motivation for this project, and then I want to show you the available data and the applied methods we applied to generate the vegetation height models. Then show you the results and verifications, and at the end come to conclusions and an outlook. So the motivation for this project, at WSL we generate digital vegetation height models since a few years. This is actually a product of the Swiss National Forest Inventory, which is also located at WSL. And we receive ADS data from the Federal Office of Topography, Swiss Topo. We receive every year around 1/6 of Switzerland's surface in leaf-on condition, and these images, these images we do the image matching and then update the vegetation height model. And this product actually is an open access product. It can be viewed in the data visualization tool of Swiss Topo, mapgeoadmin.ch, and it can also be requested in our data portal envy.ch. We get many requests from universities for master's theses and also for PhDs, but we also get requests from the private industry, like for instance from architects or even insurances. Then we also use it a lot for in-house studies, so it was for instance used to do a wall-to-wall forest cover map over Switzerland. And then it was also used to reduce the estimation error of the NFI results. And just recently there was a paper published which used multiple time steps of the vegetation height model to predict biomass dynamics for Switzerland. As you all know, there were big efforts made in the past few years to conserve, scan, register, and provide access to all the historical aerial and terrestrial images. In Switzerland, this was done by Swiss Topo, and almost all the images are now available or visible in the LE-BRIS database, which can also be viewed at mapgeoadmin.ch. And in this context, our motivation was to check the suitability to use this historical data to extend time series of high-resolution 3D vegetation information for Switzerland. Now, the data we have available at the moment at WSL, these are 4 complete acquisitions of Switzerland. They were acquired by Swiss Topo. They date from 1979 to 2007. This amounts in a total to about 40,000 stereo models. The characteristics, the first 3 acquisitions were purely panchromatic images, and in the 4th acquisition there was a change to RGB images. The average image scale during the acquisition was about 1 to 25,000, and they were scanned with 14 micron, leading to an average ground sampling distance of around 35 centimeters. Then the radiometric resolution is 8-bit, and we received all the images already joined by orientation elements, so we didn't do any orientation. The first, the third, and the 4th acquisition was oriented in the framework of the Swiss land cover statistics, because they used it for their survey, and they are quite accurate in X and Y position, but show random error in height orientation. So these errors are in the range of decimeters to a few meters. And then the second acquisition was just recently oriented with the HAP software. This was done by Holger Heisig from Swiss Topo, and these images seem to be really accurate in X, Y, and Z. So I give you a quick overview over the workflow we applied. In the first step, we generate stereo footprint geometries for all overlapping image pairs. This amounts to around 10,000 stereo models per acquisition. Then we do the image matching for every stereo model using socket Z5.6, and in there the module N-gate. Then we assemble all the DSMs of the stereo models to 1 to 25,000 mapsheet units. You see on the map the distribution of these units over Switzerland. Then we basically end up with a DSM for every mapsheet unit and for every acquisition. Then we had to develop a workflow to correct orientation errors of the DSMs. And we also do this in this 25,000 mapsheet units. And the way we do it, we take points of the class grass, herbs, and sealed surfaces from the land cover statistic data set, and the criteria for these points, so these are really ground points. The criteria is that they show unchanged classification between Survey 1, which took place from 1979 to 1985, and Survey 3, which took place from 2004 to 2009. And then at all these point locations we calculate differences between our DSMs and the Swissalti 3D DTM, which we get from Swiss Topo. Then we do a generalization by calculating the median of these differences for 40 by 30 blocks for each map sheet. And we also apply some outlier removal. Then do a spline interpolation of these generalized values. And this is actually then the correction surface, which we can add to our DSMs. Then in the next step, we assemble all the mapsheet units of one acquisition to a nationwide DSM, then take the difference to the reference DTM, in our case the Swissalti 3D from Swiss Topo, and finally we also mask buildings, lakes, rivers and other anthropogenic features, and this information we get out of the topographic landscape model from Swiss Topo. Now I want to show you some results and verifications. These are all based on the first acquisition, so from the which was acquired between 1979 and 1985. Yes. So now if you take the difference between the corrected DSM and the Swiss Alti 3D DTM, you get these nice looking vegetation height models, but to be certain that you get accurate vegetation heights and also complete vegetation height for a whole country, we had to check how the correction workflow for the orientation inaccuracies performed. Then we also looked at how complete the image matching performed over different land cover classes. And we also checked how good the image matching performed in estimating object height compared to manual stereo measurements. So here you see an example of a map sheet from the first acquisition. It's imagery from 1982. And on the left side you see the difference between the not corrected DSM minus the Swiss Alti 3D DTM, and you see that there are really that the DSM is heavily tilted, and it leads to errors of more than 2 meters for a big extent of the map sheet. On the right hand side, after the correction, you can see that many of these really big errors could be strongly reduced. Now if we look at the error distribution of these differences at land cover statistic points of the class grass, shrubs and sealed surfaces, you see that before the correction we have a median of 2.6 meters, and also the error distribution is quite wide with NMAD of 4.3 meters. And after the correction the median drops to around 10 centimeters, and the error distribution is also a lot more narrow. Now if we do exactly the same thing for the same map sheet but with imagery from the second acquisition, which was oriented with the HAP software, you see that these median and NMAD values, they are already quite good before the correction. Now then we also checked the completeness of the image matching. We did this for all the land use classes of the land cover statistics data set. These are sealed surfaces, grass, shrub, closed forest, rock and glaciers. And we did it in a way that we put circles with 5 meter radius around every point, and in there calculated the percentage of successfully matched points. And you see that for the land cover classes of interest, for our topic at least, like forest and bushes, the average completeness is well above 80%, so that's quite satisfactory. But with the data from these first acquisitions, we had really major problems to have successful image matching over grassland and glaciers. Then we also did this comparison of DSM heights to manual stereo measurements, and on the left side in blue you see the differences of the historical DSM minus the manual stereo measurements, and on the right hand side in yellow you see the difference between DSM generated from ADS data, so what we do today, minus the manual stereo measurements. And you see in both cases the DSM generation underestimates object height. But the error distributions between the two approaches and also within the different land cover classes, they are quite similar. But it has to be noted here that it's only an agreement and not an accuracy, because for the person doing the manual stereo measurements, it could also be more difficult to get correct object heights in historical images. Then we started to do some analysis, like here one example. Here you see the median of the sum of the absolute differences over whole Switzerland for the past 40 years. And so actually what it tells you is where the values are low, there were little disturbances and also little extensive management activities. And where they are high, it was the other way around. So it's typical that there was extensive forest management in the Swiss lowlands. And it could also be an indication for storm damages, which we got in the 1990s through Lothar. And then if you generate such nationwide data sets, you sometimes have some other interesting observations. And here in this example you see the Aletsch glacier, the biggest glacier of the Alps, in the vegetation height model of the 1980s, and you see that the values are really strongly negative. And then if you have time, you look more into detail. And here, just as an example, you see the glacier tongue in 1980s, 2014 and 2020. And there's an impressive change between the 1980s and 2014. And it might be a little bit less obvious that there was a change between 2014 and 2020. But then you're really curious and do some rough estimation of the changes of the glacier by taking the difference between the DSMs. And if you do so, you see that in the 34 years between 1980 and 2014, the glacier lost 1,200 meters in length, and at just a random point on the glacier tongue you see that it lost 90 meters in thickness. And if you do the same thing for the 6 years between 2014 and 2020, you see that it lost 350 meters again, and also 33 meters in thickness. And if you now calculate for the next 30 years with this rate, you see that glacier melting is strongly accelerating. Yeah, so I come to the conclusion and the outlook. So we could elaborate a highly automated image matching workflow to generate digital elevation models with a 1 meter resolution for the whole country out of these historical images. The results are plausible and the image matching completeness and the obtained accuracies are sufficient, at least for our forest applications. And it seems like the DSMs generated from images oriented with the HAP process show a higher accuracy, but almost more importantly also show a lot higher completeness over all land cover types. We didn't investigate too much into this so far, but this will follow in the next few months, I guess. And then as an outlook, we certainly aim at generating more additional time steps, also farther into the past, theoretically up to the year 1929. It is expected that the coverage will be less complete and that the generated DSMs will have less accuracy, but for our application it might still be sufficient to detect large-scale forest changes. And then we certainly also have a big potential for further analysis with the already available data sets. Actually just started to do some first investigations. And another interesting topic for us could be to combine these digital vegetation height models with the NFI sample plot information. In this way we could generate country-wide wall-to-wall maps of historical forest characteristics, like for instance biomass and timber volume. And finally we think that especially with this with the images oriented with the HAP software and also with more state-of-the-art matching algorithms, that these DSMs could also have big potential for other research topics, like for instance retrospective glacier mass balance analysis. Yes, so thank you for your attention.
So because of the fact that the last speaker is not here, I'm now in the position being the last speaker, which is a quite demanding one, and I hope, Fabio, that I will be a reasonable good anchorman to conclude this full first day of this very nice workshop. So what I'm going to present here is already mentioned by Fabio. It's only partially my work. The work is mainly done from the colleagues of the lower survey authority of the district of Heilbronn. Heilbronn is a small city which is some kilometers north of Stuttgart at the Neckar River. Quite nice, especially because they have lots of wine around Heilbronn. It's a very famous wine area. And why I'm talking on this topic is that there is obviously a need to do future or current land consolidation in those vineyards. And so the people went back some 40 years how these vineyards, when they did the first consolidation projects, were mapped. And at that time, cadastral photogrammetry was quite popular, and many of these land consolidations were done with cadastral photogrammetry. So we go back a little bit into history. This is the team, and it was a former student of me, myself, and these are all colleagues or former colleagues of the survey office of the district of Heilbronn, and I have to give credits to most of the work to them. So going back into history, so cadastral photogrammetry comes up in the beginning of the 1970s, and it was mainly driven by developments from the Institute for Photogrammetry at University of Stuttgart. This is my institute where I'm working now, but at that time it was founded and it was headed by Professor Fritz Ackermann, which I think is a very well-known photogrammetrist who now just yesterday, 1 year before, just died, 93 years old. And you see, his former student was Karl Kraus, also very well known, the famous professor of Technical University of Vienna, who unfortunately also died too early. And he, at that time, in the 1970s, was dealing with cadastral photogrammetry. And you know, there was this development in first measuring model coordinates, so doing this independent model approach, and later on the bundle adjustment comes up. And when the bundle adjustment was really operational, Fritz Ackermann himself told that unless bundle adjustment didn't become available, he has to admit that the results that have been reached with the cadastral photogrammetry based on that independent model were not as good as expected. But it changed when the bundle adjustment was there. So to give you an overview, in Baden-Württemberg, in this state of Baden-Württemberg, there were around 140 projects based on cadastral photogrammetry in the time from about 1970 to mid of the 1980s. And about 60 of them were in the district of Heilbronn. And the people there, they estimated that within these projects there were around almost 100,000 border points determined. So the coordinates of almost 100,000 points. And these points, they were all coordinated in this old historic Soldner coordinate system, which was the standard for Baden-Württemberg at that time. And okay, we know we now have switched latest to UTM coordinates, and there is obviously also a rule that all the corner points, the border points, have to be delivered in this coordinate frame. So there is a need for transformations from the old coordinate frame into the new one. And there is also other reasons why this is necessary. You see, this is, as I mentioned earlier, this is an area which already land consolidation was done in the 1980s, and now, because of the new harvesting machines, they also have to reshape the landscape again. And additionally, they put water irrigation pipes to get rid of this too less rainfall in the summer. So there is construction work in these areas, and this all affects the old cornerstones. And the people would like to know, where is my border now? So they would like to have these points into the current coordinate system. So, and then they started, as always, we are geodesists, we know transformation, so they started, okay, we have some identical points, we apply a transformation, and then we get the coordinates in our UTM coordinates. And what they noticed when they started was that in those areas where there was cadastral photogrammetry, the quality of the transformated points is much less than in other areas, and by far exceeds this 8 centimeter tolerance, which is accepted nowadays. And then they were asking, oh, why did it happen? And so they tried to firstly refine the transformation, they defined some smaller meshes, and then they also added some additional Helmer transformation following the polygon lines, and then notice it gets better, but still they saw there is some systematics which seem to follow the streets, the newly built up streets after the land consolidation process. And then they thought, oh, where does it come from? They tried to get another third transformation, and then it nicely fits, but there is a transformation, a transformation, a transformation, a transformation, and nobody really knows what has been transformed. And then they go back to what was done during this cadastral photogrammetry, and that's the interesting thing, that when the cadastral photogrammetry was solved, they didn't take the coordinates as they have been computed, but the coordinates, the net, had to be adapted to the surrounding points, so they applied some additional least squares adjustment to match the borders of the cadastral block to the already existing points, and they also apply some additional, the distances between the different border points also had to be fulfilled with the cadastral photogrammetry. So in what they essentially did in the past, they deformed the photogrammetric network, what was nice, by these additional terrestrial constraints. And so the idea was, we still have the images, so why not going back to the original observations and just try to re-triangulate the old imagery? So the first question was, okay, where are the old images? So we had, the people in Heilbronn had to identify where are those old images. And they finally found them in our national mapping in Stuttgart. And what was quite interesting, the images were cut into pieces, so no film roll, but before they were stored in a canister, they obviously were glued together again. So with some tesa, whatever it's called, yeah? And then they were rolled, and you can see you can't see in this projection, there are heavy artifacts because of the glue. So this was how they found the pictures. And then for sure the question how to scan. And luckily, sorry, this is the wrong way. And luckily, one of these almost historic scanners, photogrammetric scanners, this ultrascan was available from our national mapping. And so this scanner you already saw in the presentation of Joachim Schulz before was delivered to Heilbronn. And then they started to scan, and for sure, as it always happens when you have old materials, there are also some problems. So, but luckily, there are some technical experts which are able to repair the scanner. So the scanner is still working, and they use this old photogrammetric scanner to do the scan of these images. So altogether, it's not a big number. For them, it's a big number, but in this audience, it was just a little more than 1,000 images that have been scanned, but not all of them finally showed this painted marker points we need for getting the coordinates, and so about 600 something were later processed. And this is the typical size of a cadastral photogrammetry project. So it was always just one flight line normally, and it was a number of about 10 images taken, but only 6 to 8 finally showed the area of interest. What you can notice is that in this cadastral photogrammetry project, the images were taken with a large forward overlap, so 80%, which was maybe not standard for all the remaining projects. So in order to prove if when we take these old images in a new piece of software, whether we could achieve this high quality demands of maximum tolerance of 8 centimeter, we again took some of the data from this DGPF, the German Society of Photogrammetry Remote Sensing Camera test, which was flown in 2008 in a defined test site, this Vaihingen-Enns test area. This was the same imagery which also was used from Joachim in the scanner testing. And the good thing is here we have marked control and checkpoints, and we know these points are 2 centimeter accurate at least. So we just took a number of images, 6 or 7 out of these, just one flight line, and then we selected the typical constellation of control points and checkpoints for such cadastral projects, and then we did some statistics, and we verified that with this type of data, we can guarantee that the tolerance are well below this 8 centimeter threshold. So, and then we took the original historical data and we put them in some bundle adjustment here. The processing was done by the colleagues in Heilbronn. They took this ERDAS Imagine photogrammetry software and did process 4 projects. Basically they processed more, but in 4 projects they have reference coordinates. So it's not an easy thing to get reference coordinates, because in order to get them you first have to dig, you have to find them, because not all of them are visible anymore. And then you have to measure them outside in the field, and even if you have precise GNSS coordinates of all these points in your area of interest, you not really know whether this point is really a stable one and has not been moved by 5 centimeter because of agricultural things after the 45 years period of time. So this is what you always have to keep in mind. They try to find stable points as best as possible, but when we later go for the statistics, there might be a certain amount of error, which is because of the fact that the reference is not really stable because of changes over time. So we are comparing points in images from the 1970s to current situation in 2022. So this doesn't show any special things. And what is maybe more interesting if you really look for the differences. And we selected the differences into 4, let's call it arrow classes. And the points which have larger differences are than 8 centimeters are the critical ones. And you see it's the 4 projects, and we have about 95, 62, 72, 130 reference points where we can use to measure the differences. And you see, if you look for the last project, this Eberstadt project, there is quite a high number in this class, more than 8 centimeter. And they know why. Because this is an area where there was heavy subsidence, so there is really change in the shape of the landscape. So it was expected. And if you now change not to number of points but percentage of points, you see that about 1/3 of the points in this project has larger deviation than 8 centimeter. But if you look for the others, it's somewhere in the range, sometimes well below 10% or 13 or 15% of the points which are in this category. This means that all the rest fulfills the cadastral requirements. So the people are very happy with this, because if they would do it on a very traditional way, they would need to go to all this almost 100,000 points, try to find them, they have to measure them to give them the final coordinates, and still we don't know, is this really the historic place where this point was built up. So just to summarize, we as geodesists, as I mentioned, we are familiar with transformation, but when you do transformation to an infinity, you don't really know what is actually happening. So we lose every relation to the original elements, measurement elements. When we do bundle adjustment with historic images, we have all the advantages of bundle adjustment, because bundle adjustment not only gives us the points, it gives us the full error control. So we have the full statistics behind us, and this is very, very worthwhile for us as photogrammetrists, and it's much more accurate than just applying another transformation. The people in Heilbronn were very, very happy that they still have these old images. So for them it's clear, never throw away old things and keep them in a very good shape. The problem we have here is this problem, what we are talking about, this data has to be digitized, and we need some reliable, sophisticated scanning solution to maintain the full image information. And the last thing to mention, this is quite interesting. You know, from the past, cadastral photogrammetry was accepted as a method to get 2D point coordinates. And it was accepted by the upper survey authority of Baden-Württemberg. And when the people now came up with this new, old, or reinvented method, they had to again convince the upper authority that this is a good approach to go back to the original measurements. And I was involved in this project. It took 1.5 years, so from last summer to now. And what has now been achieved is that the person who is giving the decision gave an oral commitment that they can work this way, but it's not yet written. So it's still a little bit open, but obviously we could convince the upper authority that this is a good way to reprocess the data to get the original coordinates. And this is the end of the first day, I think.
Good morning. So we have begun studying the use of aerial images archival aerial images in order to be able to analyze long-term spatial-temporal evolution of territories, because archival aerial images make it possible to have a longer time series than archival satellite imagery and more frequent acquisition compared to topographic maps. So it's a unique and not very widely used source to study the evolution of territories and to detect changes. In France, we have aerial campaigns since the end of the Second World War, mostly. Since this period, there have been generally acquisition every 3 to 4 years. And archival aerial images are available for every part of the country and makes it possible to obtain long image time series. They have been scanned, digitized, and are made available through web services since a few years. So, such data makes it possible to have many possible use cases. For instances, to monitor urban artificialization, to study forest extension, to monitor the evolution of agricultural practices, parcel evolution, removal of edges, and also to study littoral erosion and so many other possible use cases. However, we have to cope with very heterogeneous data, considering both spatial resolution, spectral resolution, acquisition season. There was here a small example on this area. We listed all real acquisition over this part of the country during the whole aerial acquisition period, and we can see that we have panchromatic, infrared, natural color, infrared colored images. Some of them have been acquired in summer, in winter, at each period of the year, and we have also a wide variety of spatial resolution, from centimetric to metric resolution. Another possible heterogeneous source is the design of the image networks, with which are sometimes well constrained and other time less constrained. So another interesting aspect of archival aerial images is that they can provide 3D information about the evolution of territories. But this requires to perform pose estimation and then to retrieve the internal and external calibration of camera. So to do all this kind of thing, we have a project where we will have to perform geometric and radiometric processing of images, and then we have other work packages about data analysis to try to develop methods to perform change detection over time series analysis, semantic segmentation using transfer learning to be able to cope with the heterogeneity of these archival datasets, to cope with their varying quality and the fact that they can be quite imprecise, and also to deal with the lack of reference data, especially for classification. And at the end we will have end-user interaction via the development of user prototypes. So, for the moment we will focus on geometric and radiometric pre-processing. So, the constraints for this project was to be able to produce time series of auto images and DSMs to fit the other work package of the project, that is to say, the analysis of data. So, we have to develop automatic methods to be able to produce those data sets. So, considering geometry, together with scanned images, we have some metadata, a course flight plan, and course information about camera focal, information about the physical size of images and of scanning parameters. So we decided to use a usual photogrammetric pipeline, performing first interior orientation, image per image, then performing relative orientation to obtain an en-layer model involving all images, and using metadata associated to the camera, that is to say focal and approximate calibration, and then to perform absolute orientation to obtain a georeference model. This time we will also use all images and provide coarse positions provided by image metadata, but we have no ground control points to be able to do this. So, when images are oriented, we can derive final products, that is to say DSM and auto image. So we use this pipeline, and the main issues we could have would be to be able to perform a good absolute orientation, that is to say, will it be possible to obtain automatic GCPs? And also, when performing auto-rectification and mosaic auto images, we will have to perform radiometric equalization. So, when using only available metadata, we obtain this kind of results. It seems quite well, but when looking into more details, we can see that we have some important shifts. After first experiments, we noticed that using approximate camera position provided by metadata, we had a precision of less than 1 kilometer, but which was not sufficient for next steps. So, when considering DSM calculated using images, georeference, only using coarse orientation, we obtained these beautiful results, but exhibiting a strong bowling effect. So here we have also a necessity to use ground control points to be able to refine image orientation. So we developed this approach using the metadata provided with images. We calculated a first absolute coarse orientation of images. From this we derived the DSM and a first auto image, coarse DSM coarse auto image, and then using this coarse initial solution, we will detect automatically ground control points using recent auto image and DSM. So for this, we hesitated between several approaches, and at the end, we retained this one, which was supposed to be able to deal with multimodal and multi-temporal information. So, having calculated our automatic ground control points, we are able to perform a second bundle adjustment and to refine the absolute orientation of images. Then we have fine post calibration, and we are able to calculate auto image and DSM. So here are some examples of the automatic ground control points we extracted. As in the presentation of Swift Topo, we can say that our points are not very precise, but we have a huge number of ground control points, and it makes it possible to obtain at the end a quite good result. So here are some auto image results. This was the results using coarse calibration, so there were some shifts. And after the second bundle adjustment, using our automatic ground control points, we obtained this kind of result. So we can see that the data are well superimposed with recent auto image and with recent databases. We did it for several milliseconds. Then, considering DSM, we calculated altimetric differences between the old DSM and the recent one. These were the results using the DSM calculated out of the coarse calibration model. And this is the results after the final bundle adjustment using ground control points. So we can see results have been improved, even though we still have some systematic slight deformations, probably related to ill estimation of camera calibration or to small problems related to a bad interior orientation. And to illustrate the difference, this will be a DSM calculated using a polynomial model that would be applied to correct the bowling effect from the first results using coarse calibration. So we can see that using our ground control points and calculating fine bundle adjustment provides a better solution. So let's have a look at radiometric issues. Our problem is to be able to perform radiometric corrections to obtain homogeneous automosaics. So the phenomena we have to consider as a vignetting effect related to images, the hotspot related to acquisition condition, and sometimes some slight fog effect. So we consider two methods. The first one uses a parametric model, that is to say we try to estimate using type points an additive polynomial correction model for each image in order to minimize the differences between auto images in overlapping areas. It was computed at low resolution and provides this kind of results. So it's quite nice, but it has a default of sometimes smoothing locally images. Then a second model was developed. It's a non-parametric one. This time we tried to estimate a low resolution gain and offset correction grid for each image. It is done in two steps. First, a Wallis filtering is applied to each image. It makes it possible to calculate a gain and offset correction for each pixel. That is to say, it is converted to a correction grid. And then, these correction grids calculated for each pixel are smoothed using a PCA decomposition and keeping only the first principal components of this decomposition. So to illustrate this, on the top we have the raw orthophoto mosaic with very heterogeneous. In the middle we have the raw statistical equalization using Wallis filtering. And on the bottom we have the results and the proposed correction, that is to say the grid correction to go from the first to the second image, is kept. It is smoothed using the PCA decomposition, and the resulting grid correction, low resolution one, is applied to the first image to obtain this result. Another example with this time color image. So it seems to provide quite interesting results. However, we have still to study the impact of the different parameters of the method, that is to say, the size of the Wallis filter and the number of principal components to be kept to derive the low resolution correction grid. So here to illustrate this, we have the impact of the filter size of the Wallis correction. When we have a too wide window considered to estimate this correction, it is not sufficient. Here we have the good size for the window, and here it will take a too small size for this kind of corrections. So we are currently trying to automatize the choice of the size of this window. So some metric has been defined. I won't come into details, but it's current work. And to see, we have also to study the impact of the number of principal components that will be kept for the final correction. So here we have the examples of the different principal components from the PCA decomposition of the proposed correction grid. Here we can see that for the first component we have something related to the hotspot. Here we have some things related to the fact that this block was in fact made of two different acquisitions at two dates. And here we come into detailed correction. So how many principal components are we supposed to keep to have the best correction? This is not easy. If we won't take enough, we have this kind of result. And if we take too many, we can also have too detailed corrections. So it's current work in order to try to define the best number of principal components to be kept for the correction. So we obtained quite good results. We have a fully automatic method that made it possible to generate auto image and DSM time series for the study area of our project. For instance, here we have several examples of over a small area in our Strasbourg study site, but in practice we treated 600 square kilometers area and treated more than 30 image malazimes. Results are generally compatible with remote sensing analysis. We already performed some classification experiments, but they can be perfectible. For instance, we still have some limits considering the DSMs. As we said earlier, we managed to reduce errors using our ground control points and calculating a fine Bundle adjustment, but we can still have some problems when considering differences between DSMs. All those problems are probably linked to the fact that some image networks are more constrained than other ones. So sometimes we have very good results, and sometimes, as for instance for this one, there are less constraints, and then the result is generally not so good. In order to try with this, we have current work trying to find better landmarks in rural natural areas, because it happens that many of our ground control points generally fell in the neighborhood of roads, buildings, and not so much in the fields. So we tried to develop other methods in order to have more constraints in these rural and natural areas. For this, we performed a 2D registration of wider image patches. Then we performed overground filtering, removing the overground information. And then we performed DSM registration at patch level. This makes it possible to try to generate new ground control points to be introduced in the bundle adjustment to emphasize constraints on altimetric information. Or we can also use these DSM registration results in order to define a set of points to calculate and interpolate a correction surface to be applied to our DSM to have some things more correct. So everything is able to provide good results, but there are other challenges that have been recently raised, especially considering foreign correction of IGN, because we also have some collection of images acquired over former French African colonies. So, with this kind of images, everything can stop at early steps, and especially at the interior orientation step, because of various fiducial marks. Here we have an easy situation. Everything will be correct with this kind of fiducial mark. Here it can be easy, but sometimes it can also be difficult when this kind of fiducial mark superimposed with a dark part of the image, so correlation will not work very well, or sometimes with misleading image texture. For instance, in this example, we have this ray, but it can be confused with this kind of thing if the image is, if the landmark is superimposed over a dark area. And sometimes we have very difficult situation where we have some missing fiducial marks because of problems related to the image. Generally, it corresponds to physical deformation, which has led to problem when scanning the images. And by the way, this physical deformation of the images will also lead to problem when trying to reconstruct information. So, we can also have problems at early steps of the method. For instance, at relative orientation step, when type points extraction will fail. This is a problem for specific landscapes, as for example here. Here we have no problem with those images, but considering the next images in the band, we fall on water, so no type points, but we have no way to detect this, to detect earlier those images, and it can lead to small problems when performing the first bundle adjustment. We have to identify those kind of images. We can also have problems to detect type points in this kind of specific landscapes. It's quite strange. Here we have this kind of image. We only detected type points in the border of the river, so a configuration that is not suitable to perform a good relative orientation. And on this kind of area where these images are located in Congo, and we have wide forest areas. So forest areas are already generally difficult, but we also have clouds in the loop. So this is very difficult, and we don't know how it will be possible to cope with this kind of areas. Besides, the clouds will also lead to a new challenge in performing radiometric equalization of images. We also can have some correlation problems when calculated the dance matching. This can be related to image scale, noise, texture, and conservation steps, and also to the landscape. Here we have a small example on Madagascar. Well, the ortho image is not so bad. We have still not performed radiometric correction on this, but it was quite good. But the DSM is of poor quality. And having a look into more detail, we can see this is like this. And considering the image, we can see that at the beginning they had probably very smooth texture, and because they're bad conservation, because problems related to the scanning process, now we have noise, and the DSM is suffering from all this. Another problem related to these data sets are the fact that we have not necessarily recent reference auto image and DSM to be able to perform fine pose estimation. So we tried some experiments using Sentinel-2 data to perform 2D auto image registration. So we automatically find ground control points between Sentinel-2 and our old auto image. And at the end we perform a simple 2D auto image registration, which worked quite well on this kind of data. To see the results of the process. Thank you for your attention.